Hi, and let us continue with our revision of Opamp circuits. So, last time we just saw this circuit by which we can basically generate a very low feedback factor. And now let us just look at some problems with Opamp where we have RLC components and it is assumed that this Opamp basically has additive behavior. So the first thing that we have already learned is that we must check whether the negative feedback is existing or not, right? So before this input actually came, the circuit was at DC only, right? So at that point of time when the circuit is basically at steady state or when the input wasn't applied, at that time we can see that negative feedback is not essentially active in the circuit because this inductor will effectively be grounded and thus the feedback factor is zero. But the moment you apply an impulse, at that time, this feedback comes into action, right? And since the moment this feedback now comes into action, this means that this virtual ground will be activated or this virtual ground condition will now hold and this negative terminal will become grounded. Now, since this inductor is experiencing an impulse of current, since this inductor is experiencing an impulse of current, so what's going to happen is that its current will be just given by this expression, which you can easily see, and thus for an impulse it will be a unit step current, and for a step input it will be a ramp current, right? And now the only thing that now you have to see is that what will be the voltage in response to a unit step current for impulse input, and for case 2 where we are feeding a step input, we will just see that how will the circuit behave to a ramp current. So we can already understand that these will be the respective responses. There's nothing fancy in this. Let's move to the next example. Here again we have a step input to this particular circuit. So now we have to understand that what will happen in this circuit. Now, when all of a sudden, when I suddenly made this voltage jump up, what we must realize over here is again that uh, this circuit has negative feedback, right? So before initially, when this input was zero, the circuit had some negative feedback going on, right? So because of that, this node voltage was initially zero because negative feedback was active. Now, when this sudden step voltage occurred, so because of that, the capacitor experiences a sudden voltage change across its plates, right? Which is equal to delta Vx, right? Now, because of this sudden sudden voltage change, which is basically a step function rather. My bad, I rephrase myself. The sudden voltage change is basically step input. That's why from the simple Q equals to CB, we can establish the current from the capacitor, which is the impulse current. Now from this we can understand that this entire impulse current now will flow through this resistor because an inductor won't allow an impulse current to flow through it, and since our parallel path is present, so this impulse current can flow through this current, right? So all of this impulse current will flow from here, and at the output, what we'll observe is a negative impulse initially. Now after this, the moment this has occurred at t equals to zero time, now the capacitor won't allow any will now not allow any current across it, right? Because the moment this change happened, now as we'll converge as we'll converge since it's basically you can see that the current of the capacitor is impulse, so now no current is flowing here, which implies that by simple case here no current will flow here also to the output, right? From this what we can understand is that this initial impulse voltage that's got generated at the output, this will be generated also across the inductor, right? Because no current is flowing through this branch. So all of this voltage will appear across the inductor. Because of all of this voltage is appearing now across the inductor, as a result of this, now this inductor will also generate a current of its own, which we are calling as I loop. This I loop now can be given by the integral of voltage developed across the inductor, and thus now we are seeing a unit step, right? So the current is now a unit step, and now since this is a unit step current, so now what we can find is the value at 0 plus time, which is just simply this term multiplied by r, and there will be additional minus sign because this terminal is 0. And so what we get is a positive value, which is Vx r square C by L, right? Simple. And at infinite time, we already can understand that this current that we established, this current is just for t equals to 0 plus time. But we know that intuitively, since now no current is flowing in this branch, no current can flow here, so this current will just loop and decay out, right? So this current will decay out with time constant equals to n by 2r. Great. Let us now look at another example. Here again, we have had a step input to a capacitor. So again, we can understand the current through this gap will be an impulse. And now this impulse current has two ways. Either it can flow from here, either it can flow from here. So initially, all the impulse current will flow through this resistance, ignoring the inductor, and thus we'll have some initial output voltage, negative output voltage, which will basically be an impulse, as you can see here. After this impulse is transpired, now all of this voltage that appeared across and between these two resistor terminals, that there will also be some voltage because of which there will also be some voltage across this resistor, and as a result there will be a voltage across this inductor also, right? And that will also be of impulse in nature. Right, because we can understand by voltage division, that half of the voltage will appear across this resistor. These two resistances are equal, and thus there will be some sudden voltage appearing across the inductor. By virtue of this, we'll have a unit step current which will initially develop, which will be the initial value across of current through this inductor. And similar to this scenario, since here was impulse current, it will cease for positive time. Here also there will be no current later. So that means that now this current it developed across the inductor will just loop in this guy, and thus eventually, just like this example, this voltage also because of this loop current will decay out, right? And it will decay out with tau equals to L by L. So these are some examples I thought that we can discuss. Now, before going into positive feedbacks, commit trigger, and why stable multivibrator and maybe oscillators, I just want to discuss some other concepts. For example, realizing a non-linear function with an op-amp. So, how the basic idea behind this is that to realize a non-linear function, what do you mean by non-linear function is that Vi basically so basically V out depends on Vi in a polynomial expansion form, right? It does not only depend upon the linear term, but it also depends upon square, cube, and so on. So how we can realize a non-linear function of op-amp. The main idea is that you basically put the op-amp in negative feedback, and you have your beta has as some function of x. So because there is negative feedback active here, so this guy is also vi. This basically implies that if you feed v out to this function, the output is vi, right? So alternatively, what you can write is that v out is equals to inverse of that function uh, which has an argument of v in. So that's some quite novel way of realizing this v out. So there's an example now over here, and how this example goes is that we have a multiplier over here, and we are multiplying some input, say m of t. So what will happen is that here we are observing vi. Vi is here is empty. So some this v out multiplied by empty is vi, which alternatively means that v out is vi divided by empty. Quite cool, right? So now here is a small example as of how we can implement uh, voltage squarer over here. So that's what we have tried to do is that here you have some output which is V out. Now this there is another op-amp, and this op-amp also is a negative feedback, which implies that this V out is equals to this V out, right? Because this terminal is V out, so this terminal also becomes V out, and now V out times Vi. So basically, you're feeding input at two places. So this guy becomes what? This and again notice the direction of the multiplier also. So basically, this multiplier is that it will have input this way and input this way, and here you will observe the output. So this node is V out, and this node multiplied by this node is V out, which implies that what should be this node? This node will be Vi, as I have written over here. And since again this circuit is also, this op amp is also negative feedback, this basically implies that Vi is equals to V out by Vi, which again translates to V out equals to Vi square. Right. So this was a small thing that I wanted to discuss. Now that being said, again, I just wanted to just discuss about all I have for negative circuits. I just want to really quickly revise that so that in maybe next video we could discuss about positive feedback also. Now here what I have is logarithmic amplifier. You have already seen this, and you understand that its output is basically proportional to the natural log of input, right? So here we are seeing that this is the particular circuit that we have, and the feedback loop we have basically a BJT in basically common base configuration. Now, the exponential characteristic of this BJT is why we are getting this logarithmic behavior to begin with. We could also have a diode here actually, and if we just cleverly place some diodes over here, then also since they have exponential current, so it won't be exactly just a diode in feedback, it will be just a clever arrangement of diodes so that we can bring about again a natural log behavior of output with respect to input. Yeah. So here in this problem, this problem is a stability problem, and what it is trying to basically say is that this op amp is real, which means it has a real gain, it has some poles, and this is the pole which is given, and this op amp is basically modeled by two poles actually, and the second pole is far away. It's 10 times this unity crossover frequency, and it has a dominant pole at omega p. It has a DC gain of A naught. And now what is being asked is that if we feed this kind of an input to this op amp, then what will be the output? Right. So this input basically transitions from 1 volt to 50 millivolt, and this is the ideal characteristic. So what will be the output of the op amp? Again, since we don't have much data about the DC gain of the BAM, but let us anyway proceed with the analysis. So first of all, we should be able to write we should be able to write expressions for current. So here, basically, despite the fact that this op-amp is said to have this kind of a body plot, still we are anyways applying. We are still anyways applying virtual short, assuming that the gain of the op-amp is very high. So what we get is V minus 0 by R, this is the current, is equals to minus Gm times V naught, right? So minus Gm times V naught, why? Because that is basically the base to emitter voltage of this BJT. So minus Gm times V naught is equals to this current, right? And now, if we look closely, so this V out term can be said as equals to minus Vt, natural log of Vi by S by R. Now, one question I want to pose to anyone who is viewing this is this being equated to this guy is fine, but is writing this correct? Because this is for small signal only, right? So writing is this correct? Is something that I want to pose to the viewer if anyone is watching this. But we know this for sure that since in our analysis it's a large signal analysis, so this is still short equal to this, but is writing this also correct? Anyways, when we equate V by R to this current, what we get is we know this guy quite easy to establish. Cool. Also, now we can establish the loop gain also, right? So what will be the loop gain? The loop gain that we are writing, here we are basically first of all expressing our feedback factor as we are expressing our feedback factor basically as the voltage here and the voltage that is appearing here due to this voltage. So what you understand is that because of the application of voltage over here, we are having some voltage over here, which is basically what? Which is basically just the gain of this BJT, right? So basically the idea is that when we are finding feedback factor, you just apply some signal here and you observe the signal appearing at its negative terminal. Alternatively, what you're just checking in a way is that you're applying some input signal over here and you're checking the output, which is basically like checking the gain for a common base. uh, for a common base BJT, right? So which is just equal to Gm times R, and Gm is IC by Vt, so this is the beta. And now you can express your loop gain as As times the beta, which is just this guy, right? Simple as that. Now the given op-amp beta we have, and this beta we can now express. Now we know that IC by R current is flowing in this direction. So we can understand that this IC by R is also equals to what? Vi. So that's what I have written. It is equals to Vi by Vt, which basically implies that now we can have some constraint on the value of beta, right? Because now beta is Vi by Vt and Vt is 25 millivolt. This implies that for an input of 250 millivolt, my beta is 10, and for an input of 1 millivolt, for 1 volt, which is our basically input, one phase of input, our beta is 40. Cool. Now, since we are to comment upon the stability in this problem, so we know that stability basically depends on the phase margin. So we can easily express our phase margin as this. That phase margin is 180-degree plus plus the phase of this loop gain. So it just turns out to be 180-degree minus tan inverse omega u by omega p minus tan inverse omega u by omega p2. Cool. So now, what we need to understand over here is that the pole locations and all are still fine, but the issue is that as the beta changes, because this Bode plot is basically what this is the basically the Bode plot for open loop gain where beta is one, but when beta changes, what will happen? When, for example, when beta increases, this graph will move up, right? This graph will move up, which basically implies that our unity gain frequency will be higher. If you look at this expression, if unity gain frequency is higher, this basically implies that this angle will increase, this angle will increase, which implies the phase margin, if it was initially 90-degree, it will decrease, right, with increasing beta. So from this, what we understand is that the higher beta becomes, the more worse our phase margin will be, correct? So that is something that I wanted to convey. So here, as you can see that for beta equals to 10, what we are seeing is that we are basically our phase margin is degrading down to 45-degree and we are having ringing. Now, how did we converge to these exact values? So what we need to understand is that this omega u, which is the unity gain frequency, we must be able to understand that what is the formula of this omega u. So what we understand is that this open loop unity gain frequency for a first order system is approximately given by DC gain times the beta times its pole. So we can understand that it is a directly proportional to beta. So if beta increases by 10x, this guy also increases by 10x. And that's how we came up with these numbers. It's quite easy to do, right? So what we understand is that for one particular input, that is 1 volt, beta is 40, which implies system becomes more unstable. And for lower input, the system is more stable, right? What this implies is that for this kind of an input, the output should kind of look like this, that for 250 millivolt the ringing is less, and for 1 volt more there is more ringing, right? So this is the kind of output that we can expect, and this would have otherwise been the output for an ideal op amp. So this was the stability consideration that basically we had to see in this logarithmic amplifier. And here again we are seeing that beta is greater than 1, and this is an example where basically the feedback block is also an amplifier, and that's why we are having such kind of a scenario to begin with. Cool. So now from this we understand multiple things about op-amps, also about its internal structure. If we have some context about how the internal structure of op-amp comes about, so we can understand easily why things are the way they are. One was that we understood that this unity loop gain frequency is a very important term because on this only the phase margin is calculated, and with changing beta and DC gain and the pole, this unity gain frequency also varies. And if this unity gain frequency is higher, then that means our system will also go into more of an instability. That is something that we understood from this. Great. Now, here, what we have stated as a remedy is that we can basically reduce the beta of this circuit so that we can have a more stable response. A way of doing that is that we have just introduced an RX over here. And alternatively, what you can understand is that this will then the feedback factor just looks like a common base VGT with degeneration. So that's what I have written, that an extra degeneration term also comes into picture. So if beta, now initially it was GM/R, but now it becomes GMR by 1 plus GMRX. So if GMRX was 10. So now the beta will decrease by 11 times. So that means the stability will really improve by a huge margin. Cool. Now let us just discuss one of the last scenarios, and then maybe next video we'll start our discussion for positive feedback, and maybe then this Opamp circuit thing can be wrapped up. Cool. So this is a scenario where we just compare simulation with reality. So if you just look at the circuit, here, what we are saying is that there is just a unity feedback, and we have applied some input over here. All right. So, what will happen is that in simulator, what will happen is the simulator will just calculate this numerically, and what will happen is that it will just say that V out is equals to some the gain of the op amp times V out minus Vi, which basically implies that V out is equals to this guy. And since the gain is quite high, so alternatively, it will just appear as if V out is equals to Vi, and this circuit will actually seem to act as a unity buffer. If you recall, in reality, a unity buffer is it looks kind of like this. Right? That's how a unity buffer looks like. Both of these resistances are same. In reality, this is how a unity buffer actually looks like. The sign is inverted, of course, but this is how a unity buffers kind of looks like. But here in positive feedback, we are claiming by simulator that this is a unity buffer. But in reality, what happens is that this wire has some delay and it also has some parasitic associated with it. So it is not this much straightforward that this output voltage or this output voltage exactly appears here instantaneously and everything is so much instantaneous in nature, right? And also the fact that this op-amp right now is acting as an ideal op-amp, but in reality it is a transfer function, right, which depends on the location of poles and zeros. So in simulator, what is recommended is that you can model the same picture by using some capacitors and resistances to model the wire and capacitances and resistances. It is something that we also do in our normal simulations also, that we add some parasitic capacitance and resistance on our own without uh, first bringing the circuit to layout, so that in schematic only we can estimate how much the wire parasitics will hurt us. So we intentionally put additional capacitances and resistance in the circuit just so that we could plan design in a more optimized way. And then when the circuit actually goes into layout, then we just try to basically pre-estimate that how the parasitics will increase in the. So a good design practice is that in designing and when doing simulations on design level and transistor level or in system level, we just try to add some parasitics and resistances on our own, which account for all the parasitics which will happen in the layout process. Cool. Now, let us just also discuss then what will happen in reality. So what I have said here is that in reality, wire has some delay, right? And V plus does not change instantly. As I said, that if here it is V out, this guy won't instantly become V out. So what will happen is that Vi, if you say if Vi is del V, then initially V plus will be equal to 0. And because of this kind of a difference, our V out will go into saturation. Now, when V out goes into saturation and Vi is del V, so now it will kind of try to stay there only because now there are no dynamics in the circuit, right? And when this input is negative and this V out, this V plus node is initially 0, then the circuit will just get stuck at minus reset. So that is the basic idea. And this is a scenario is also kind of similar. It is actually identical only to the Summit trigger, which actually we will discuss in the next video, which is a good, great frontier to explore what positive feedback of circuit, which is basically the Smith trigger, and then we'll talk about the stable multivariate. Before that, on concluding note, one of the last things that I want to discuss is that non-inverting integrator undergoing open loop to closed loop transition. That's the last topic just that I just want to discuss over there. So just let us say that this switch closes at t equals to 0. That implies that this circuit suddenly became from open loop to closed. This implies that initially when this circuit had 10 volt had as input at its positive terminal, we would have just given the you would all know that the Opamp swing limit output is limited by its swing by its DC biasing, right? So here since it's plus minus 15, so output would have had been 15, right? And the moment this switch transition happened, what will happen? The moment this switch transition happened, this circuit then will try to act as what? It will try to act as unity buffer because now suddenly this negative feedback is acting. So suddenly we'll observe that this output will now drop down to 10 volt, and then it will grow back up in steady state. And again, since at steady state this feedback is no longer valid, so it will go back again to 15. And that's what I have tried to show here by some mathematics, right? So here basically V out is equals to A times 1 plus SRC. So basically what I have done here is that I have done some hand calculation for my assertion, and so yeah, so that's what I have written, and you could have just solved it mathematically, and you would have established that this circuit will have three regions of operation. One is that it will act as a unity feedback circuit, as I said, and thus 10 volt will be the initial value, and then for t equals to 0 plus time, it will act as an integrator for a short while, and then it will then quickly saturate back to 15 volt, since it will then become open. So that is what I have basically trying to establish over here. Last note that I've written here is that when finding the output impedance, put a current source to basically determine the output voltage, because a voltage source test can change the node voltage and remove the effect of feedback. So now this is something that we can understand only in practice. So it's just a note that I've written for myself for future, but this will be more obvious to us when we try to solve questions posing us with such kind of a diagram. Great. With that being said, I just put this video to an end, and in next video we can finally end the discussion of Opamp circuits when I finally wrap things up with the Smith trigger and and with the stable multivariate. And thanks for watching, and maybe I'll see you in the next video.